but I'm going to tell you how I can model unknown dynamical systems with neural differential equations. So, can you see my screen?
You have to share your screen.
Yes.
Okay, good. So, a dynamical system is any system that changes through time according to some rules. For example, the weather or the economy, all examples of dynamical systems. But these dynamical systems follow a certain equation defining their behavior. If we don't know the equation of a system, we can't simulate it. But I think the solution is neural ordinary differential equations. Now, some background on what these are. First, ordinary differential equations are anything of the form du dt, where u is the state of the system, is equal to f of u comma t, meaning some rule based on the current state. So it's relating the rate of change of the state of the system to the current state. So a neural network, there's a lot behind these, but for the purposes of this project, we can just think of a neural network as a black box. You put in some numbers and you get out other numbers, and you can change the parameters in the neural net until you get out the numbers you want. So a neural differential equation is combining these two, as the name suggests. You replace that rule in the differential equation, that function of the current state, with a neural net. So the neural net takes in the current state of the system and gives out how much it should change in the next time step. So to produce results from a differential equation, you integrate it, which is you evaluate the equation once to get the current rate of change the state by that much, and then repeat the process until you get all the way through time as long as you want to go. For a neural differential equation, you have to do a similar thing. Because the neural net only gives you the rate of change, you still have to add that to the current state and repeat the process for however long you want to simulate. Now, this seems counterintuitive because you could just do something like this, as you see on the bottom right. You could just plug in the time and initial condition and get out the full solution you expect. And there's a few good reasons for not doing this, actually. But essentially, it's because the physics, we can almost assume, takes the form of a differential equation. And so enforcing this structure on the physics makes it more likely we'll get coherent and logical results. So to test my hypothesis that neural ODEs can learn to the physics of simulating unknown systems, we apply it to the Lotka-Volterra equations as an example. So here are the equations in the top left, and their wolf and rabbit populations are W and R, and the Greek letters are just constants. And on the top right is a graph of a population over time from these equations, starting at some initial condition. For each species, population is the y-axis, time is the x-axis. And we can also extend these to 3 species, adding in, say, bears to the system, where you have this third equation and more terms on each of the other equations. And the graph for that looks like this, with 3 lines for 3 species. And as you can see, it's no longer the simple periodic thing that we had for 2 species. It has more complicated non-periodic effects. So to do this, I used Julia programming language, and I wrote code to first get the real equations that we have and evaluate them for truth data to train the neural network on. Then we create a neural network and create a loss function comparing the neural network's output to the truth data, and then we train it using automatic differentiation until the neural ODE starts producing results that look like the truth. So I did this in stages of ascending complexity to see where a neural ODE, if at all, would stop working. The first is the most simple. Can a neural ODE match a 2-species Lotka-Volterra model, that is, wolves and rabbit population in a forest? So here's some examples of code from this. In the top right, on the top left, we have the Lotka-Volterra function, which is the real equations, and you might see similarity to the actual equation there. And on the bottom left, we have creating the neural net, and that creates this bottom right structure of this neural net. So after training this system, here on the top, we have a few examples of training. At first, the dots, which are the prediction, are far from the lines, which are the truth. And so the neural ODE isn't doing very well, which makes sense. We haven't trained it. But after more and more training, as we go to the right, the dots align with the lines, meaning the neural ODE learns the physics of the system and is able to simulate it. And then we apply it to a new set of data with over a longer time span, and you can see that the dots still line up, meaning it really learned the physics of the system and can extrapolate from what it knows. So the next problem, the next stage, slightly higher complexity, more difficult for the neural ODE, is training it to match a 3-species Locker-Volterra model, except one of the species, the bears, is hidden from the neural net. It doesn't ever get to know the population of the bears. So to do this, I can guarantee that it needs at least a little bit more information. There's no way I could do it right without even knowing the bear population. So we add in this recurrent channel that it doesn't ever get told the bears, but it could just predict the bear population, and that would just give it a little bit more information for itself. So after training on a testing data, this looks like this. The wolf and rabbit populations, the dots are right on top of the lines, which means it's successfully predicting those two populations. Now what's going on here? The bear population dots are way off the line. And this is actually expected. Although you might think it's bad, it's perfectly fine. Remember, we're not telling the neural ODE what the bear population is, so it doesn't know how to model the bear population. What you're seeing there in that line is just some piece of data that the neural ODE is sending to itself. It's just the internal workings of the neural ODE. And since it still matches the 2 variables we did measure, it's successful. So next, we're kind of cheating in the last experiment because, as you can see, it actually starts with the bear population. As you can see, at time 0, the prediction is right on top of the truth for the bear population. It knows the initial bear population. So what if we take away even that? So this would be like a system that it doesn't even know there's a 3rd variable. And think about applying this to another model. This is like applying to a system that you don't know the equation for, and you don't even know all the variables for. So there could be a whole unmeasured variable in the system that you don't even know about. And neural ODE might be able to do it. So to do this, we need something to initiate that recurrent channel. So we have a separate neural net outside the neural ODE, which takes in a few data points from the wolf and rabbit populations and gives out another number that to initiate the neural ODE. Now, after training, this looks like this. Again, the wolf and rabbit populations are right on top of their lines for the prediction. So it's successfully predicting the wolf and rabbit populations very well and over a much extrapolated time span, much longer than it trained for. Again, the bear population is off its line, but that makes sense. It doesn't even know the bear population. There's no way it could match that line. So we've successfully proved all of these. Neural ODE can match a 2-species Locker-Volterra model. It can match a 3-species one, even if some of the data is hidden from it. And it can match a 3-species model with an entire component of the problem hidden from its view, which you couldn't even write down with a normal equation. Systems like the weather, for example, might not have real equations because of their complexity, and there could be unmeasured variables that we don't think play a role. But a neural ODE can actually learn to simulate systems like this anyway. So now to clarify a few things. Earlier, I was just showing you one plot as the dots approached getting right on top of the lines. But I was actually using batches because the neural net could just learn to draw a line that looks like that, right? Well, if I train it on batches of different initial conditions, as you can see, all these plots on the top are completely different. They have completely different shape. And so it has to learn to match all of these at once. And so the only way it can do that is to actually learn the underlying physics of the system and not just learn how to draw a line. And I also, for testing data, apply it to a much longer time interval to see that it extrapolates past the time interval it learned on. Still it's good predictions. So in each of these problems, I showed you how I solved it by adding something to the neural ODE. And I've actually invented these neural ODE architectures. I've never seen them written about before. And so why am I inventing neural ODE architectures instead of someone at MIT or something? Well, the tools I'm using to do this, which includes the Julia programming language version 1.0 and some of its packages, are extremely new. They've just come out. And so everyone's getting access to the tools for doing this all at once. So I just happen to be the first one to get to it. Now here's some examples of my code. Again, the top right, you see creating truth data, and middle, you see creating a neural network. And you can see the structure of that neural network, the size. You see the neural network, there's a diagram on the left, and this has over 2,274 free parameters, which is a lot. And it's especially difficult to train on that many free parameters. So it would be impossible to do that, in fact, without automatic differentiation. This automatically carries through the gradient on each of the parameters on the first evaluation, making it incredibly easy to train. It wouldn't be possible without it. So in conclusion, I've successfully created a neural network that can learn to model systems with unknown equations and, in fact, unknown parameters and completely unknown components and variables. So I've demonstrated that this could be extremely useful to systems that we don't fully understand. Even if there's a whole underlying variable that we don't even know about, we can still model it and learn the physics like this. So again, going back to this image I showed you on the top right, why wouldn't we just do it like this? Why wouldn't we just put in the time, initial condition, and get out the final state of the system? It seems like that'd be way more efficient. We'd only have to evaluate the neural net once, and then we'd be done. Well, there's a good reason, a few good reasons. First, this integrating the neural ODE means we can enforce conservation laws. There's actually no conservation laws in terms of wolves and rabbits, but in other cases, this is very important. Also, automatic differentiation, like I said, this is used for back propagation to automatically get the gradient on each of the parameters and then change it so the answers are slightly more correct, and doing that repeatedly to train a neural network to get the correct physics. So, like I've said, neural networks, this could be an extremely powerful tool, and I've created neural ODE architectures that could be used in physics we don't understand, even if there's a whole variable that we don't even know about. So thank you. Do you have any questions?
Thank you very much. Judges, the floor is open for discussion.
How did you design your neural networks? Neural networks typically have a number from one, a number of intermediate nodes. Sometimes they go with, multiple layers of intermediate layers. And how did you decide what, the parameters for your neural network?
Right, so the actual size and shape of my neural network, the number of layers and things like that, is shown in this diagram and this. This is the actual code creating it. So in general, I took a shape already used in literature in other papers for doing similar things, and used that because it's sufficiently wide and large enough to approximate anything. It could be smaller. I didn't test very much varying the number of layers, but I just used this size for all my experiments.
How long did it generally take to do a training run for one of your experiments?
So neural net could train to, for the testing plots I've shown where it successfully matched, it took just a few hours of training, and that's without GPU acceleration. So for example, the dots are practically perfectly matching the lines, and that's just maybe an hour of training from almost nothing on batches of initial conditions. It actually goes, I found it goes much faster with batches because it can do it in parallel rather than training it on a single instance and cycling through different initial conditions. That's actually a lot slower.
Robert, this is Sharon DeLand. So similarly on the ODE solver, how did you pick the solver? How did you look at time steps? How did you have confidence that it was getting you to a valid solution? What kind of testing did you do there?
Right. So I just used a built-in solver from a differential equations package. You can see it in my code here. Let's see. Yeah, so it's just very quickly solves it like this. It just does, you know, one function. It's basically from a built-in package. It's a higher order one because I found it could go unstable. And in fact, I had to experiment a little bit with setting the relative tolerance so it didn't go unstable. But generally, I just didn't have to worry about that because of the package.
Hi, this is Stephen. So you're training against a time series generated by the ODEs, right? And in your first slide, you said you have to know the equations before you can simulate something, right? Or
Yeah.
So the alternative for, say, a LAHS is an agent-based model that have interactions and rules and interactions. Have you given any thought of how you might discover the rules and interactions? And it may not be a neural network, but have you thought about like the alternative way of simulating and discovering an underlying model?
Right. So the LAHS equations are really an example problem for wolves and rabbits, just to demonstrate neural ODEs can work on really anything. But the equations, the neural ODE never gets the equation. In fact, it knows nothing about wolves and rabbits. It doesn't know how they interact at all. So the wolf-rabbit interaction is no part in the system. The neural net still learns how the physics of the system without knowing a thing about wolves and rabbits or their interactions.
Let me ask it a different way. So you have a macroscopic, the ODEs kind of describe a macroscopic description of the problem, whereas an agent-based model is more of a micro description. So I understand that, you know, this is a general ODE solver that you're approaching, but have you given any thought of how to find the micro model, a micro model that would satisfy this?
No, I haven't done anything but really putting a neural net into a differential equation, a general neural ODE, because most physics happens to take that form. Most things can be described with a differential equation. So this could be applied to anything, not just wolves and rabbits. I haven't looked into any sort of modeling of wolves and rabbits.
Okay, thanks, Robert. Just one follow-up too. So you're using a swish activation, is that?
Yeah, that's correct.
You chose that one?
In fact,
and then how did you choose that one?
So I pretty much just experimented with different activation like Tanch and things like that until it sort of just trained better and more quickly. And so I left it with Swish.
Thanks.
So Robert, this is Dave Janicki. In looking at these models and taking what Stephen was just asking you about, I want to sort of change perspective a little bit. Very often in ecological systems, as your example is, there are lots of parameters that we don't know what their influence might be, whether they're an influence or not. And so, you know, I like your initial approach. The question I have here is, have you thought any about how this system would operate if you started feeding it some noisy data rather than the very regular sort of summarized physics model you have? And have you thought about any of that, where instead of feeding it very regular data, you've got maybe more and more noise, which would be very common in an ecological system, where the bears aren't always every place and the wolves and the rabbits aren't necessarily evenly distributed?
Yeah, so that's a really important question, because right now we're using just the actual equations to get truth data, right? But in real life, to learn the physics of the system, the whole point of this is you don't know the equations already, so you take measurements, and those could very possibly have noise, like you're saying. So I haven't actually tested adding noise to the system yet, but I definitely thought about doing that, and I want to do that if I continue this project in the future.
Yeah, very good. There was an interesting paper in the last month or so. I don't read Science and Nature in sequence, but there was an interesting discussion about some of the areas around Mount St. Helens where they've got a potential risk of a dam failing on Spirit Lake. And the ecologists are all very worried about putting a road in. And those are exactly the sorts of things that you'd like to be able to model. In fact, I would claim that the ecologist going in and measuring is also a perturbation that you'd like to know whether it's important or not. So moving forward with doing these uncertainties and trying to figure out how well you can drive your model even in the summary physics state is very important.
Yeah, so this could be applied to all sorts of things. You're right. Who knows what it could be applied to? Maybe there's some systems that we don't even realize follow neural ODEs, like that dam thing. Who knows? All sorts of. In fact, there could be a huge number of unknown variables, and this could potentially still work to model systems like that.
So Robert, a question. This approach that you've taken, what do you think the limitations of it are? In other words, what do you think it would fail at doing?
Neural nets, there's this thing called the universal approximation theorem of neural networks, and essentially what it tells you is a sufficiently large neural network can approximate almost any function. And so given that most physics can be described with a differential equation, all physics really, and that differential equation just has some function relating the rate of change to the current state, and that function can be anything, and a neural network can approximate any function. It seems like this could be applied to anything, really. Perhaps there's
so Robert, question here. When you were modeling you had to introduce a recurrent channel. If you don't have that recurrent channel, would your approach fail?
Yes, it would, and I tested it with that. I discovered that recurrent channel is definitely necessary because it just can't get the right answer without more information.
So if you tried to model a completely different ODE and you didn't have the right channels, would this work?
Well, it's pretty general. The recurrent channel can represent any unknown variable and perhaps combinations of unknown variables. So adding enough recurrent channels and enough variables, it should be able to model any system as long as the number of recurrent channels is more than the number of variables.
What if you, instead of adding a third species with, the kind of predator in a predator-prey relationship, what if you added a completely independent kind of third factor like climate data or something?
Yeah, that's a good question. So it could have, like a third factor like that could have a completely different effect on the system. It could have a much more complicated effect too. But as long as if it's represented by a number of variables and we have enough recurrent channels, then the neural network should be able to learn any physics, even if it's a combination of all sorts of different things, even if it's not describable by normal equations. It should be able to learn any sort of physics.
Robert, I just have a quick, just more technical question. On GitHub, you have some Python notebooks and your Julia code, right? So where's the Python notebook running on GitHub?
What do you mean running?
It's actually executing, as far as I can tell, when it's making the plots and bits.
Oh, right. So, yeah, you can download the code from GitHub and run it on your computer, and then it'll output some plots and show you some plots, and then you can save those. And a few of the plots are already saved in the figs folder, which are the ones I used. So I just executed that on my own machine, and then upload the code and figures both.
Okay, yeah. But it's also executing. If you just look at a Python notebook on GitHub, it generates. It looks like it's generating the figures. So it's just kind of
Right. So in the Python notebooks that are saved, it saves the output with it. So it's just downloading those into the notebook. It's just showing you what's already run.
I see. Thanks.
All right, judges, we're out of time. Robert, thank you so much. Good luck. Enjoy the rest of your day.
Thank you.